slide. Let me turn up the volume. All right. Good morning and happy Tuesday. Welcome back from break. Um, this semester, of course, you're here for AI, and AI might be or might not be what you think it is, right? There's an unfortunate naming for generative autoencoder deep networks as being AI. And while, yeah, that's part of AI, it's only a very tiny corner of AI, right? And so I really strongly encourage you to read the syllabus so that you know exactly what you're getting into this semester. Hopefully, it will be a lot of fun. Um, so before we begin, I like to start all of my modules with the administrative section. I will always display what is due. For this week, there's the reading. I won't read the slide, you can read. And also Project One auto released last night. Project One is purpose with getting you used to the programming environment, specifically the AutoGrader. I've invested the time in sort of cramming on how to use AutoGrader on the instructor side because of the sheer number of students in the class. Again, we have 39 students, many more of you than me, and I'll try really hard to remember everyone's name. Some of you I know, some of you it's like a reunion from other classes. Um, but I'll try really hard to study your freshman year picture. Can you update that? The ID picture? You can't? No? All right, interesting. Because for some of you, it does not look the same, right? But nonetheless, I will stare at the pictures and try to learn all those names that I don't currently know. Some of you I do already know. But please make sure you jump on the assignment early. And if you have any questions or something's not working with AutoGrader, I tested it many, many times. But if something glitches, please do not hesitate to reach out to me. Does everyone have a Gradescope account? You do? Okay. Has anyone not used Gradescope before? Yes? No? All right. So please look at that early. And it has three relatively few moving parts questions for Project One. And it is purpose with getting you used to how you submit things for this class for the projects. All right. Any questions? No? All right. So as a species, humankind, we've come pretty far from our early beginnings as hunter-gatherers. And if you can imagine, just simple existence took a lot of work. If you wanted rabbit, you had to go run for a week or more to try to catch this thing. And then once you caught this thing, you had to skin it, you had to prepare it, and then you could finally eat. Couldn't just go to the drive-through and say, let me have a chicken sandwich, right? Or rabbit sandwich or whatever you want to call it. And, people are pretty amazing. Some of us are quite strong. And I looked this up, and my goodness, 782.6 pounds bench press just once. That's really, really strong. And we're very proud of how strong we can sometimes be. But compared to other examples, other animals, other species in the natural world, we're not that strong. Take, for example, this red male kangaroo. It looks like one of those cheesy "come at me, bro" kind of things, Jim Bro, right? Um, but this kangaroo, red kangaroo, adult male, stands about 6'5", is 200 pounds of pure muscle, and can puncture your bowels just with a swipe of its claws at your midsection. That's horrific. Now, bench pressing 786 pounds is quite the feat, but the silverback gorilla weighs about 300 to 425 pounds and can lift 10 times its weight. Now, so we might think we're strong in some cases, but we're not that strong compared to other examples in the animal kingdom. Now, some of us are quite fast. Usain Bolt. And this record, I had to look it up, still stands 9.58 seconds for the 100-meter dash. And this record still holds. That's blazingly fast. But when we compare ourselves to other examples in the animal kingdom, we're not really that fast. I can't imagine thousands of pounds rhinoceros charging at 30 miles an hour. That'd be horrific. Now, of course, a friend of mine says you don't have to run faster than a rhino. You just have to run faster than your friend, right? Well, I thought it was funny. But anyways, and when we look at the best that we can do in terms of our speed, well, we're just barely faster than an elephant, but not quite as fast as a domestic house cat, because there are several examples in the animal kingdom that are stronger and faster. So, our question of the day, and my question to you, kind of get your thoughts. So, if we're not very strong, we're not very fast, what in the world do we as a species have going for us? So, I'll put it out to you. Yes, Chris? I'm sorry? Language. Ah, language. And what does language do? What does it enable us to do? You ever thought about that? What does language do? Yes? Oh, well, let me get you behind Chris. And what's your name? Luke. Luke. Share ideas. Ideas. Language and ideas. How about you? I'm having trouble hearing you. You pass down ideas. So ideas can kind of live on, right? That's called culture, right? Some ideas um, get modified from one generation to the next. Some ideas, new ideas enter, and some ideas kind of die out. So you talked about sharing, you talked about ideas, you talked about this idea of culture, cultural icons, things that are passed down. Anything else? Any other ideas? No pun intended. Robert, we have brains. Okay. And how does our brain enter into this? Not a trick question. How does our brain enter into this? Nikki? Mm-hmm. Tools and C and innovation. A lot of words here, huh? Sorry? Problem solving. A lot of interesting things. Okay. So our brains, our ability to create, our ability to share what we create, our ability to describe and represent what we create. Okay. Interesting. And so, yeah, we've come a long way. Our ability to create, our ability to think, to develop things, more than compensates for the fact that as a species, we're not too strong, we're not too fast. But my goodness, we can think. And so this idea of thinking captured the attention of early mathematicians and later computer scientists. And in the mid 50s, early to mid 50s, the field of artificial intelligence was hatched. And so it's all in pursuit about trying to unpack and get sense of, make sense of this thing we call thinking, this thing that gives us our advantage relative to other entities in the natural world. Okay. Any questions? No? So, this idea of intelligence, as Robert mentioned, it starts with our brain. And the brain is a really amazing, beautiful piece of machinery. It only has a single algorithm that it implements for this thing we call learning. And it doesn't matter what types of sensations, whether it's sight, whether it's touch, whether it's taste, comes streaming into this thing. It just works the same. And it comes up with representations for things that it encounters as the organism it inhabits moves through the world, this machinery. Okay. Well, even in infancy, and I'll ask you the question, is an infant quote unquote intelligent? Yes. How is it intelligent? Because an infant can learn any language on earth with no textbook and no classes, right? How is it intelligent? What would you think? What are your thoughts? Yes, it can learn. What is this learning thing? What does it mean to learn? Have you thought about that? Learning. Hmm. What is learning? Okay. And then, as the maturation process happens, these infants in their development, they're endowed with a number of reflexes that help bootstrap or create good conditions for learning. There's something called the tonic neck reflex that they're born with. If you take an infant and gently, emphasis on gently, turn its head to one side or the other, an arm will pop up like this. Now, the reason for that is to precondition this infant to attend to visually things in the environment at arm's length. Infants like to put a lot of things in their mouth. They like to grab things. And that's part of the learning process, trying to uncover how the world around it works. And we have strict definitions for what I mean by how it works. Now, when the infant matures, the infant's primary interaction is with its caregiver. And so it's looking to the gestures and the expressions of its caregiver for a notion of emotional state, fear, happiness, displeasure, etc. So then later on, as the maturation process continues, the motor machinery starts to come online. And so now this infant is starting to waddle, starting to move around, can now go places in its environment, further learning how the environment works and its relationship in the world around it. If I act in the world responds back to me. And you build an account for all of these types of reactions, i.e., the learning you alluded to. So then after that, you go into kindergarten and later grammar school, and now you start to socialize. You develop this notion of friends and enemies and sharing and not sharing and fair and unfair. And moreover, you exchange these cultural icons, these ways of behaving with other similar organisms who might have learned slightly different things in the context of their caregivers in their home environment. So then eventually you go off to college where you are, and now you learn a whole bunch of ideas. Maybe some of your thoughts are challenged. New things are learned, both technical as well as personal. And then you graduate, you go off into the world and you do this adulting thing. You learn how to be a grown person, right? Well, if that's insulting wholeness, I'm already grown. There are a lot of things like you might start your own family. You might get a mortgage, move across the country, move to a different country. There's a lot of interaction at a different level that happens at this adulting stage. And then, even in the latter years, as your physical machinery begins to change and things will break, you learn to adapt to that. You might have to wear glasses like I do, or maybe your knees don't work the way they used to, and you compensate for this, but you still acquire new skills like pickleball. If you've ever been to a pickleball court, I've been by one, and there are a lot of older folks who really enjoy pickleball. Anyone play pickleball? Yeah, it's kind of fun. I've played squash before, but that I don't like getting hit with that ball. That's not fun. All right. Any questions? No? All right. So this learning thing, the brain, it enables us to do all sorts of stuff. And some of you alluded to some of that stuff. You said sharing, you said communication, you said language, you said learning. Okay. All of those things. So we're going to not do all of them. We're going to set up some frameworks and approaches that allow you to implement programs that exhibit what we call intelligence. And there's some rigorous definitions that we're going to put in place along the way. Okay? All right. So this is the main text. When you go off and look for the book, you can find it more cheaply used in a number of places. I'm a fan of driving down costs as much as possible. Please know that there's also a global edition. It's similar but not the same. Okay, so just keep that in mind. There's also the ebook version. I prefer atoms over bits, but to each their own, right? But please make sure you have the text. I've laid out the entire schedule notionally for the semester so that you know exactly what you're getting into, including the reading assignments. Okay. Any questions? No? And so um, the assessments, we're going to have five programming projects worth cumulative together 45%, three homeworks. The homeworks are purposed with reinforcing theoretical material, worth total 9%. We have a midterm. I know 19% is an odd number, but it had to add to 100. We have a traditional final exam. Because of the class enrollment, I can't do a final project. If you've ever taken one of my classes before, I usually have a final project, but it's just not possible with the numbers. But I will have most likely the graduate students do a final project. I just have to be able to manage the large census for the course. And class participation will be 2% of your grade. How I'll do that, of course, is you showing up to class, but also your participation, right? Including discussion on Slack. Please, if you have a question, even if your question might seem quote unquote naive, promise you on the instructor side, for every question you think is naive, about a third of your colleagues in the class had the same question. Right. So I really want to be able to leverage those interactions to benefit everyone in the class. And so there's class participation. The grading scale is in the syllabus. And also, in addition to 160 being a prerequisite, you should know how to write software in Python. There are some resources on the course Canvas site if you need a refresher. And so I like to run my classes digitally so that you can sit at home in your pajamas and hand in your work and do stuff with the class. I do post the recordings of the course. And again, I'll stress that's not a substitute for you attending class. Okay. Any questions? No? And so topics, we'll look at agents and definitions of agent environments, the so-called state space formulation, uh, learning as search. We'll include stochastic elements, look at probabilistic and Bayesian reasoning, something called Markov decision processes, sequential decision making, the reinforcement learning framework with two different algorithms, value iteration and Q-learning. And then we'll also talk about ethics and societal impacts of AI. And so this course is kind of a survey of various AI techniques. And I would be remiss if I didn't say that deep learning is a tiny corner of AI, and there are other courses that will specialize in that, like the DSCI 225. Okay? All right. So, policies. I strive really hard to maintain a professional environment. I'm fortunate to have been a research scientist in industry, distributed systems, R&D, and then mathematical modeling after that. And so I really, really work hard to maintain professionalism. It's important for me that the classroom environment is welcoming to everyone. And I, as a frontline employee, have a duty to report, right, for all forms of harassment. Please make every effort to be here on time. It's a large class. Message me on Slack if you need to schedule office hours outside of what's posted for my office hours. And this helps me to help you. And I ask that if you do so, please kind of let me know what it is you'd like to ask me so that helps me to prepare. You say, I have a question. Okay. Question about what? Okay. All right. Any questions? No? All right. And so my late policy is I don't accept late work. I realize and acknowledge that sometimes life gets in the way. Please make sure you start your assignments early, and I will do everything in my power to help you to succeed. Should an issue occur, I only ask that you reach out and you communicate. Okay? Your programs have to run and compile. I reserve the right not to score them and just assign a zero and move on if it doesn't run, right? I'm not going to debug your program for you, unfortunately. Um, I value a distraction-free environment. There are many people who do. Side conversations are painfully obvious because we can hear you. Please, if you have something pressing to say it to the whole class. Okay? All right. So I will help you succeed. If I need to Zoom call you at 8 p.m. at night, I'll do that. But please do your part. And that means engaging the material as quickly and as much as possible. I highly encourage you to discuss, debate, argue about the material with your colleagues in the class. It's always more fun when you have a running buddy, so to speak, right? My dog is my walking buddy. I don't run like that anymore. um, but also communicate and do not struggle in isolation, right? Um, your wellness is important to me. In fact, I'd say your health and well-being is more important than some darn class, right? I had a career in industry before coming into academia, and one of the things we learned, at least in the groups and organizations where I worked, that behind every role is a real person, right? And so in college, you're going to learn technical things. Of course, that's obvious, AI in this course. You're going to learn some professional things like presentations and time management, and you're going to go through some personal growth. And so with this work-life balance, of course, sometimes things happen, and mental health is certainly an important aspect of health, right? And there was a report by the CDC a couple of years ago that said 1 in 4 college-age young people has struggled with suicidal ideation. And please know that there's no shame in asking for help, right? I'm more than happy to help you, but I am certainly not licensed, nor am I qualified to help in that way. But there are resources on campus who are, right? The Center for Counseling and Personal Growth. I'm more than happy to point anyone, and students have in the past, to these critical resources. They have fixed hours, which are typically business hours. There are other resources that are 24/7, right? So please, there's no shame in reaching out for help. Okay. And so, illness. I believe that sharing is caring, but not if you're sick. If you are sick, please feel welcome to stay out of class and not get everyone else sick. And also, in this environment, some people choose to wear masks for various reasons. Please respect their decision. You never know what's behind what someone's experiencing. My father passed away in May, and he struggled with some serious degradation in health. And so, of course, being an instructor, I would wear a mask and I had to be disease free for 2 weeks before I could go and visit him. Right. So that's just to say you never know what someone's going through. So please respect one's decision should they choose to wear a mask or whatever. Okay. All right. Any questions? No? All right. And so accessibility. If you require accommodations for accessibility, um, don't just tell me, and that's your private information. I fight hard to respect the Federal Educational Rights to Privacy Act, or FERPA. But if you require accommodations, you need to go to the accessibility office and initiate their process. None of your constructors can do anything for you unless you start that process. Once you start that process, what happens on our side is we get letters from the accessibility office, and it affords you the ability to have 1.5 time for exams as well as proctoring in the accessibility office. Okay, so please do that early if you need those services. Okay, and also please bear with me. Of course, the course is significantly oversubscribed. I'm actually pretty surprised that so many people are interested in AI. Um, People usually aren't that interested, but I guess it's popular now. And the last time this course was taught was 5.5 years ago. So it's effectively a new course. The world is very different right now. But the other consequence of that is that we don't have a TA, no PLA, because they've all gone on to industry, and I can't convince them to come back and be a PLA. But anyways, um, we're also going to be navigating Gradescope. This is my first time using Gradescope, so I've gotten a crash course on how to use Gradescope on the instructor side. I'm more than happy to help you with some of your systems issues, but please know I haven't used Microsoft Windows really in over 20 years, right? I'm primarily Unix in various forms. I also wear many hats. Well, I'm not wearing a hat now, but I'm department chair, whether you know it or not. And so there are often unscheduled things that happen all the time, right? I'm on various committees, and of course, I run my research lab. My students in my lab can attest to you how chaotic things can get sometimes. Okay. Any questions? No? All right. So, what actually is this thing called AI? Well, when we think about the human brain, human development, human learning, and human growth, it's really just the thought can we mechanize this thing called intelligence? But in order to mechanize it, you have to understand it. And there are a few definitions and models and things in place that help us get to that. And so we got a puppy back in September. And this puppy is from a shelter that I volunteer at about 3 times a month. I help exercise dogs and assess their temperament and stuff like that. So if you're looking for a pet, I don't know, you can't have it in the door, but if you're looking for a pet, let me know. But nonetheless, this is a pit bull terrier mix, and her name is Raja. My daughter named her after, as I understand, the tiger from the movie Aladdin. And Raja, like many dogs, is learning. This dog is exhibiting high level of intelligence. So one day I bought her this 8 puzzle toy, and all of the tiles around the sides, they slide. They can either go vertically in one space or horizontally, revealing a compartment, and you put little dog treats in that. Okay. And so, this is a first level learning toy, and they can increase with difficulty. And the idea is that the dog learns how to slide these tiles and get this treat, this reward. So, of course, getting that reward, that treat, that's a good thing. And so, part of this learning process will formalize with reinforcement learning is how to ascribe the actions that you take proportionately to this reward at the end. It's an interesting problem. But nonetheless, Raja's sentiment is, I shall defeat you. Right? And she did so handily. And so she engages in perception. She sees it, she smells it, and she knows it's there. She's inputting sensations from the environment around her, and she knows that this is something that she desires. She also selects the appropriate actions. She walks over to this toy, she grabs the toy, she paws at it. So she can both see, hear, and smell and taste. She can select actions in order to try to produce a desirable outcome. Okay. That's another aspect of this thing we call intelligence. And so, language, some of you mentioned the ability to define language to ascribe this meaning to this concept for things you encounter in your environment. So I say treat, treat, and she associates that word treat, even though she doesn't speak my language, she associates that with this particular experience afforded by this device. She also does reasoning. She decides, okay, well, I'm not going to sit on my dog bed. I'm going to go over there and interact with this thing. So she can evaluate decisions. That's another aspect of this thing we're calling intelligence. She also performs learning. She knows that rather than randomly whacking it on the floor and randomly pawing at it, that there's certain set of decisions that more quickly lead to this desirable outcome. Okay. She also makes decisions. She can evaluate the order in which she does things and choose the right set of actions in order to arrive upon this desirable outcome. And then she can do problem solving. She knows that she's revealed the treat in one section. She can sniff around and pick out where the next treat is and act accordingly. So she can make decisions. But the thing that really kind of floored me is she decided, I'm going to short circuit all of that. I'm just going to break the tray and just reveal all of them and not have to spend 10, 20 minutes trying to go through this whole process. So the moment she figured that out, of course, when you give it to her, the first thing she does is goes to breaking it apart in order to reveal all of the compartments. So this is just to illustrate to you different aspects of this thing we call intelligence and crafting programs that engage in these processes is the subject of this course. Now, certainly we can't go through every part of AI. We can only go through some. But the goal is to set you up with the right framework so that you can then, after the fact, pursue other things that we did not cover. All right. It's a big, thick book. Okay. All right. Any questions? No? You ready? Okay. So, what is AI? So, let me ask you, what is a model? If I were to say AI is about the development of models, what does a model do? Have you thought about that? Let me get your ideas on that. What's a model? Yes. An LLM is a type of model, but let's abstract, and thank you for answering. What does a model do? Question. Yes. It solves a problem. Okay. So a model solves a problem. An LLM is a type of model. It's a very complex model, very effective model. Any other thoughts on that? What is a model, Nikki? Ah, it tries to recreate how we would think. Let's modify that definition a little bit. It tries to recreate how things behave, right? Chris? hmm So it recreates, and you can express a model many different ways. Math is one popular way, but there are other ways by associations that you can use to represent a model. So AI involves models. Now, not just any models. These models are for the purpose of creating programs or mechanizations, algorithms that can do thinking, perception, and action. Now, when we talk about action, it's not just a physical action. It could be a software action. Your mechanism can live purely in software, and an action would be doing something purely in software. It could be sending a message over a network or measuring, for example, the flow of packets through a router, for example. And so to support these models, you need a representation. You need a way of formulating the scenario over which you're going to be doing this thinking, perception, and action. Let's take this example on the right, or the left, I should, yeah, left. In your mind, you swap. This is an eight puzzle state space. And an eight puzzle, kind of like that dog toy that Raja defeated, has a bunch of tiles labeled one through eight. And there's an empty space, and you slide these tiles either up, down, left, or right in order to place them in numerical order, left to right, top to bottom. Now, with this representation, you'll notice that to go from one node starting at the root to another node traversing down the tree, that represents the resulting state of this eight puzzle after you've taken a particular action, right? And so with this representation, you can perform thinking, perception, and action in order to solve this eight puzzle, regardless of the initial configuration. Let's take this example on the upper right. This is the tangent space of the Riemannian manifold. You can think of it as a faceting or tessellation of a smooth surface with a bunch of planes. Now, with this representation, it facilitates comparison of data sets very, very efficiently, right? Let's take this thing on the bottom, this transformation of points in feature space. It allows you the ability to simplify the type of math that you need in order to classify or cluster data. And so, in order to create a model, you need a representation. And part of our goal this semester in the course is to go over a number of representations that afford you the ability to mechanize certain models or ways of doing things. Okay? Right. Any questions? No? No questions? All right. So, what are you going to do? Develop an understanding of representations that help you build programs that are quote unquote intelligent. Now, of course, when you have a representation, there are going to be certain constraints. When you traverse from one action to the next for this eight puzzle, certain types of transitions from one state to another are not possible, right? And so every representation is going to have constraints that bound the types of problems and the ways that you can solve certain problems. And of course, these representations and constraints are targeted at the implementation of programs that can think, perceive, and can act. So we're going to be looking at different methods, different frameworks, and different algorithms. Now, to the engineering crowd, AI is about building quote unquote intelligent programs. They can make decisions of their own percepts, what they input from the environment. But for the scientists, like computer scientists, we're looking at computational accounts of intelligence. For example, what is culture? How do you represent culture? How do you take this representation and use it to do something? And then what are the metrics to say something, some representation is successful or it's not successful? So the engineer and the scientist both use AI, but we have different purposes. Okay. All right. Any questions? No? All right. So let's take a look at a couple examples. Self-driving cars. Now, self-driving cars, I remember when I was in grad school, it was in the research lab. And then when I was in industry, some of these features started to make their way into deployed products, which is pretty amazing. And so self-driving cars are instrumented with a lot of sensors. Sensors that measure distance, sensors that measure speed and bearing, sensors that measure position, sensors that measure what's around it. Now, all of this together with this type of system, you have to make decisions online. Now, when I say decision to online, it means while this system is thinking, your model is thinking about what's going on, the world is constantly changing. This is very different from something like chess, where you make a move and then the world changes in very predictable, known ways. Now, what makes self-driving cars and the driving problem difficult is that you have a bunch of other things around you in the world that are changing, and how they change, you could think of as being governed by a probability distribution, but this distribution changes, and it changes in ways that you won't always know. So that makes it a very hard thing. So I'm going to show you an example of a simulator of lane changing. And with this lane changing, there's no sound. It's going to do what's called center return. So, when you change lanes, much as you might not think, you pass on the left, right? And then you get back into your lane. Now, some of the things that are going on, there are different vehicles, which it has to sense. And that's done in a simulation because you simulate it before you deploy it in a real system. And that green yoke is a spline interpretation ahead based on the curvature and the speed. And you use that to determine safe distance, both for driving, following, as well as for the lane changes. And so you can see here, it's slowing down because the car in front of it is slowing down. And then it speeds up once there's a safe distance between the car and itself. So what this green spline is doing is something called path planning. It's evaluating what is safe to do based on the sensors that are continuously inputting information about the environment around it, including the lane changes. And so when the lane changes happen, well, you know what the lane widths are from your computer vision system. You can do what's called lane keeping, staying in the center of the lane, while at the same time sensing the cars around you. And when you're a safe distance for the lane changing, you then take that spline, set a new point, and recompute the polynomial, and then sample points along it, and then control your steering actions to satisfy those sample points. And all of that happens in split-second decision, again and again and again and again. And so no two lengths of roadway are the same. You can't say if I see a car exactly here, I do this. If I see a car there, I do that. You have to use probability, right? Stochasticity is rife with what's called non-stationary world model. Okay. Any questions? Okay. This is an example, and there are two people in this room who have already seen this, of a foraging application. And this was done, well, partially no, 2 years ago summer, and then during the semester last year. And it's searching for grasshoppers in the environment. Now, they weren't pre-programmed where the grasshoppers are. It wasn't pre-programmed where the box is. And so it uses something called YOLO, a computer vision detection algorithm, for object detection. And then it extracts the pixels, computes the principal axes, aligns the manipulator with the principal axes, and goes and grabs it, and then memorizes where the box is based on what it detects, and then delivers the grasshopper to the box. And so you can have an arbitrary scattering of grasshoppers in the environment, arbitrary placement of the box in the environment, and this thing is perceiving, it's thinking or deliberating, and it's acting, right? Okay, any questions? And so we won't do robots per se, but in this class, we will use a Python-based Pac-Man game environment. And the one caveat is this is not a game programming class. There are other classes for that. We're using this Pac-Man environment inspired by UC Berkeley to give you a framework for building models for thinking, perceiving, and acting. Okay. Any questions? No? And so I wanted to give you an example of perception, right? To drive home this idea of not just looking at the environment, but this idea of analyzing what the content of your environment means. So on the left, we have a heart-shaped stone. On the right, we have a heart shape in a latte coffee drink. Now, do they look the same? No. Do they look different? They don't look and they do look the same, right? So what are we seeing here? If you were to look at the pixel color distribution, well, the stone is more gray. The coffee is kind of more brown and beige. They kind of don't look the same. But what is it that looks the same? Well, if we look at functional relationships, self-similarity among the pixels in these objects, there's some similarity there. And that's what arises. And so when we think about this idea of functions over things, that's an unimaginably large space of things that we can choose from. And so when you do perception, you're analyzing not just what is in your environment, but trying to find this notion or encode a notion of what it means. And you'll be doing some of that within the Pac-Man environment. Okay? All right. There's much more descriptive power when you evaluate relationships. So I wanted to give you kind of an example of that. This idea of self-similarity is exploited in convolutional neural networks because what you can do is you can capture certain aspects of what's called the aboutness of an image or other piece of data, whether it's a brush stroke or the way colors work, or it could be the relationship spatially, geometrically between pixels in an image. Okay, so I'm going to give you an example of this. I took a picture and I tessellated it to 40 by 40 cells, and then I randomly exchanged pairs of it 5,000 times. So I'm going to ask you an unfair question. What's in this picture? Anyone? No? Yes? Uh, I can neither confirm nor deny. Okay. Yeah. Mm, No, what's happening is that you're all hallucinating what you think it is, right? Um, but nonetheless, what I've done is I've destroyed the relationships among patches of this image. So let me help you out. I'm going to do you a solid. How about 20 by 20 random exchange? So I dramatically better the resolution. Anyone want to venture to guess? Make it easier? Yes? Land? I'm sorry? Animal. How do you know? What kind of animal? It looks like an animal? Okay. All right. Hmm. You getting kind of warm? Yeah. Okay. Exactly. All right, so you keyed in on something you recognize. Yes, Nikki. Fingers? Okay. All right. So 10 by 10. Does that make it easier? Yes. Timing. Playing with a toy. Yes. So where is it? What's it doing? You said playing with a toy. All right. So, okay, playing with a toy. So let's do 5 by 5. Does that kind of come into your memory of something you know? Yes, Barbie. A stuffed animal? Yeah, there's a stuffed animal there. Okay. And this is the original picture. It's Raja. And so what you have experienced was this idea of what perception is. You know certain spatial relationships that are consistent with objects that you've experienced in the past. When I broke that, you lost that. And then as the resolution got more and more coarse, spatial relationships started to emerge. And then you said, aha, I see an eye, I see a dog toy. Well, it kind of somebody said a couch. Like, how'd you know that? But anyway, so this is the dog. All right. And so imagine then if we take this idea of different aspects of spatial relationships that could be the color or the relationship between colors, and we learn that or we memorize it. Now we can take new images and we can apply those styles to it. So I went and did that with Raja, and this is the Van Gogh version of Raja, right? And then I said, oh, you know what? Let's continue on. This is the Scream, Edvard Munch version of Raja. And this one is my favorite. This is Mona Raja. I like how the dog toy is sitting there in her arms. But nonetheless, this idea of perception deals with functional relationships between parts of your data with other parts of your data. And this is a very large space that gives you descriptive power, and networks that do style transfer are doing exactly that. Okay. Any questions? No? All right. And so another big win for AI applications, um, looking at relationships at multiple scales, has to do with language translation. It's not just the word root to word root translation. It's looking at the relationships certain number of hops away in the sequence of words, the semantic meaning. And it's very, very good these days. And so, this idea of perception is that you don't just look at the data, you evaluate functional relationships between parts of the data. In Pac Man, which way is the monster moving relative to me, etc. Okay. Any questions? No? All right. And so, AI has been used to do things like control nuclear reactions. I don't think I would want to be the scientist that does this because you only have very few opportunities to make mistakes. But nonetheless, I'm fairly certain they simulate and they have small controlled experiments before they put in on large experiments. Um, there are a lot of differing opinions on large language models and AI in general. Some are for, and some are against the use of these models. Now, like any tool, I remember when statistical search engines became popular in the early 90s, InfoSeek was one of the first ones. They said that's going to ruin education, right? It's just a tool, but how you use this tool is often the difference. So as a scientist, I kind of am in the camp that, yeah, I don't think it's so bad, but you want to make sure that your application is sound. In particular, in K through 12, a lot of schools use Google Gemini and, I'm sorry, Google Classroom, and Gemini is being rolled into Google Classroom. And it's been shown that these large language models shunt critical thinking, right? And so, again, like any tool, it's really important to understand and develop best practices for how it's used because there is a human impact. Okay. The monetization, as you've probably seen, you can go on any job board, and there is a large, large amount of money being poured into AI infrastructure and AI applications. And if you were to ask me, should I get into AI? I would say, yeah, getting into AI is a good idea where the big opportunity is now is in the so-called agentic applications. And so you're using the APIs for these different frameworks for enabling so-called intelligent programs. Okay. All right. Also, there are some dangers in play. There are some that are looking at using AI or large language models in particular for mental health counseling. I think that's a really bad idea, right? For various reasons. And so when you deploy and develop these AI programs, these intelligent programs, it's really important from a design standpoint to think about both the cohort to whom this thing is targeted, but also the impact on those people. As a scientist or engineer, it's your responsibility to do so. Okay? All right. Any questions? No? All right. And so this one, there's a lot of displacement happening, and I thought this one was particularly interesting. Is anyone familiar with Tilly Norwood? No? Yeah. Okay. Okay. So there's a large ethical problem. First, there's the displacement on human workers, but then the other question is who gets to decide the likeness, culture, and the behavior associated with this work? If this thing wins an award, well, who gets the award? Is it the programmers? Is it the folks who created the generative AI model? So there are a lot of complex questions. Just because you can, there's still an impact that it makes. And so you can create an entirely digital character that can behave and that can do things. And I encourage you to watch the video from the URL. I'm not going to play the whole thing. And so it's your responsibility as an engineer or scientist to think about the impact of this. Because also, when children consume this content, they don't get sarcasm. They don't know what's real from what's not real. And in fact, I've been teaching my daughter about deep fakes by having a video of the president praise taking my class. Oh, I love that AI class. It's so well designed. It's a beautiful class. So something so outrageous, she knows it's not true. But when you consume content online, you have to trust but verify. You can't always believe what you see, but there's a real displacement here and some very interesting societal impact types of questions. Okay. And so AI has also kind of turned creativity on its head. Art that's autonomously created can't be copyrighted. Okay. So if you create an AI piece of music and you win an award, someone can copy it. Well, how did you create this? You had to create it by taking things that already exist. So there are copyright issues in place. You're using somebody else's content in order to create a new work without necessarily the attribution or paying the due royalty that person is entitled to. So lots and lots of interesting societal questions. It impacts economy, impacting politics, impacting law, public perception of what AI is. And there's a lot of hype for entertainment value that happens with various AI technologies. It's also impacting the workforce. A lot of jobs are going away because of AI being able to do them quite well. And so this idea of rationality is what we're after, this idea of human intelligence. And what does human intelligence really mean? You could think like a person, but do people always think correctly? No. It kind of looks human if you make a few mistakes here and there. If you go into a large language model and you ask it the same thing multiple times, the answer is a little bit different each time. That makes it kind of look human. You can also do what's called thinking rationally. It's not just thinking, but the right sequence of thoughts. Some think that is what human intelligence means. Well, you could also act like a person, right? You can run, and there are humanoid road races and track races and things like that. And sometimes people don't act correctly. Sometimes people stumble and they fall. You could also act rationally, and that's not just acting like a person, but doing quote unquote the right things for some definition of right. So there's a performance criteria, doing the right thing at the right time. There are experiments now with robots that will fold clothes. So doing the right thing at the right time, you have to do certain things to the shirt before others in order to quote unquote correctly fold clothes. Okay. Um, so rationality is defined as the acting such that you achieve the maximization of some defined goal. So that needs some notion of a performance measure. And part of what we're going to do in this class is look at different types of performance measures in a Pac-Man environment. You also need a notion of utility of outcomes. How good, not just what you do, but how you do it. For example, with autonomous driving, the goal is to get to the destination. You could get there quickly. Yeah, that might be good. But getting there quickly might be a very uncomfortable, harrowing ride. Instead of driving and stopping, you skid into your destination, right? You're getting there quickly, but it's not the most pleasant of experiences. And so rational means acting to maximize some idea of a performance measure. And because the world is stochastic, it's not discrete. Well, some are discrete, like chess, but the real world is stochastic. You can only do it probabilistically. So maximizing the expected utility, not necessarily the outcome of how you might think. So if you really wanted to kind of coin what AI is, you can think of it as a computational account of this thing called rationality. What are the right things, and how do you do the quote unquote right things, and how do you measure this idea of right, your performance measure? Okay, any questions? No? And so there are different perspectives. Some look at the skills. You should be able to do certain things. Either you make mistakes or you don't make mistakes. Nonetheless, you learn from experience. You're not going to uncover the right way of doing things each time you're presented with a task. Maybe you're caching certain landmarks along the way so that you're not trying to uncover what the right thing to do is every time you encounter that. Moreover, the ability to adapt to new situations, right? That's another perspective from a skill standpoint of what intelligence means. There's also an embodiment perspective. Embodiment means you have a physical form, you have a body, and you're also situated, meaning that you have some relationship to your environment. I push on my environment reacts back to me. And it's the understanding of how that environment transitions or evolves over time that tells me or informs what I can do and what the quote unquote right things are. If I'm trying to walk to that doorway and I go straight through the doorway and I bump into this table, the environment is telling me you shouldn't go straight that way. And so this idea of embodiment is an important aspect of rationality and hierarchy. You build up basic skills and use those basic skills to solve higher level problems. If you play sports or whether, pick up or organize sports, you do drills for a reason. You're building up these skills that are going to be necessary to select from when it's time to perform in a competition. So situated in the world, you need perception. In the real world, it's computer vision, maybe speech recognition, and you also need the ability to you are situated, and that's to manipulate and to locomote. Now, I'm a roboticist by training, but certainly your robot can be a soft bot, meaning purely software implementation. And in that case, the environment in which it lives is that environment where your software is deployed. That could be a soft bot that lives in a data center, optimizing network flows. It could be a soft bot that's controlling the lighting, for example, sensing when people walk into the room, turning on and turning off the lights. Okay, any questions? No? And so intelligence is based on this idea of the design of a so-called rational agent. An agent is something that acts. Rationality means that it acts in order to achieve a notion of a best outcome. And there are two basic flavors of rational agent. You can be a reflex agent or deliberative. Reflex means that when you recognize certain things from your environment, you play a particular action. Deliberative means you're making evaluations. They're both different and they have their place. If you've ever seen a Roomba robot vacuum, there's a lot of reflex in there. The later versions with cameras, there's some deliberation. They're figuring out where the dirt is, what the dirt looks like, where in the room they are, and they build models of what is happening dirt-wise and location-wise in the house. And so rationality can be mathematically defined, this idea of utility or the goodness of an outcome. And so AI you can think of as being the study and definition of these agents, these actors that quote unquote do the right thing. And you have to decide what right means or what desirable means. And you express that through your performance measure. Okay, any questions? No? No questions. All right. And so we have two tasks that I'll kind of show as an examples. There's chess and there's self-driving cars, autonomous vehicles. Chess is a large combinatorial space. It's discrete. It's large, yes, but it's discrete. And so acting in chess means looking at the configuration of the board, considering legal transitions between configurations of the board, and deciding which configuration you believe will lead to a desirable outcome, right? A position or configuration where you win or your opponent can no longer move, right? Um, with driving, of course, there are other agents in the world and they move in ways that are not really defined. You have to sense them continuously, and you're building models in order to make decisions, like we saw with the lane changing, about what is the quote unquote right decision. Now, of course, rationality is hard with autonomous driving because there are all sorts of factors that are unmodeled that can occur. You can have other drivers that don't do the right thing. They don't indicate when they turn. So you have to react to that. You could have equipment failure. Uh-oh, my brakes don't work as well as they should. But there's also this idea of what's called value alignment. Yes, you could get there to your destination quickly, but is it a smooth ride? Was anyone injured? And one ethical question, suppose the car is definitely going to collide with somebody. Do you collide with a parked car on the street or do you collide with the pedestrian? Well, you have to make a decision. Now, of course, most people would say, I collide with the car on the street. How do you make that decision with an autonomous car? Because it's not modeled, right? And so when you're in the real world, things like autonomous driving, you have to make that value judgment because certainly as the maker of the software and the manufacturer of the automobile, you're liable should somebody suffer injury from the use of your system. Okay. All right. Any questions? No questions? No. All right. And so I was gonna kind of skip history, but I'll just maybe go to one or two slides and not belabor the point. It is very important to know some of the history. Even some of the people recognized as being um, major influences on deep networks fail to acknowledge some of the pioneering work. And so in 1950, Alan Turing um, had an amazing investigation. If you think about the time, It was very forward thinking. Can a machine think? And the idea was, can you simulate a machine in a machine and particularly mechanize the thinking process? And so he came up with this idea that was later called the Turing test. And it said, mechanization is intelligent if a human interrogator can pose questions to it and you can't tell if the response is from a human or not. It's sort of invisible to the interrogator. They can't tell. Well, that's no longer what happens modernly, but if you've used large language models, they're pretty good at giving you seemingly reasonable answers. But if you ask it certain types of questions, it'll sound great, but it's just pure garbage, right? So we're not really there yet. And so, in order to do that, you need some perception. Natural language processing, you have to store representations of knowledge, different nuggets of information that are true or false that you can rely on from which to reason to give an appropriate answer. You need to be able to deliberate and adapt to new situations. Um, and so there was a bunch of work with introspection was really, really important in the early 60s. This idea of looking at thoughts, the thought process, the sequence of thoughts as they proceed in time. And so when you do decision making, you're not just evaluating what you're going to do now, but you're looking and considering the impact, and we do this in reinforcement learning, of on the future states of the environment based on your decision one step, two steps, or possibly K steps away. Um, there's a bunch of other work that happened with neural networks. Some major players, Minsky and Edmonds, McCullough and Pitts, Hebb, which kind of deals with reinforcement learning and back propagation. Arthur Samuels, Checkers player, he was at IBM when he did that work. But one of the interesting things that happened in the summer of 1956 was the famous Dartmouth AI meeting. And so they collected together, I think it was 10 or 20 researchers to come to Dartmouth and spend 2 summers, and they were going to solve the AI problem. They were going to come up with a complete mechanization of what intelligence and what thinking is. Now, I encourage you to go look at the link. It's an interesting proposal, but some of the things that they came away with, I list there, using language, neural networks, theory of calculation size, so complexity theory related to thinking and reasoning, self-improvement that grew into machine learning, abstraction, so knowledge representation that can be interpolated forward to new situations, randomness, and creativity. How do you propose things that aren't necessarily the best in hopes to try to uncover things that potentially can lead to better solutions? So-called exploration versus exploitation. There are many risks and benefits to AI. There are some applications in autonomous military vehicles that are controlled by AI, surveillance in following, tracking, and deploying things based on this tracking, decision making. There are AI-based systems that look at loan approval and the and parole in the court system, right? Judicial information systems don't always make the right decision. In employment, right? They look at resumes using AI, and that can be very much gamed. Life safety systems, controlling the electrical grid or water delivery systems, and AI and cybersecurity, that's been done for about 15 years already, various AI systems. And so there are a lot of applications, there's a lot of monetization, and we're going to use this class as an opportunity to teach you some of these models, some of these representations, and some of the algorithms for you to be able to implement programs, in our case, the Pac-Man environment, that think, that act, and that do perception. Okay. Any last questions? No questions? No? All right. So with that, we'll stop there. Please take a look at the syllabus, and I'll see you all on Thursday.